Okay, hello everyone and good afternoon. So I will present our new tool. Actually, it starts with Flash, so it fits with the FLASHTagger, open source web application for top-down protein identification. So far we talked about for the proteomics bottom-up, but this time it is top-down, and people now talked about like a lot of top-notch deep learning, but this is kind of legacy skill. So I hope this interests you. So let me briefly compare bottom-up versus top-down. So in bottom-up, given this protein, we digest the protein into small pieces, and each piece is analyzed like individually. But in top-down, basically, this digestion step is skipped, and we have spectrum from intact protein, and you want to go back to the protein identity as a whole. And top-down is so very well suited for the proteoform resolution study, where proteoforms are different molecular forms of given protein, including genetic and splice variants and modifications. I'm sorry, why this is just okay running. So top-down fits well for the proteoform level study. And these days there are a bunch of different protocols, as you see in the right side. But now the tool is more or less focused on native MS or native top-down or complex down, which is quite similar to the native top-down. Native top-down. So basically, native MS is the protocol where protein molecules are ionized while just maintaining their native conformation. So basically, it skips the denaturation skip, and non-covalent interactions are also skipped, also maintained. And often native MS is subject to the further fragmentation for deeper level information. So this is called native top-down. And so native top-down can be used for protein complex and protein ligand binding, site localization, and conformation studies. And typically, native top-down workflow is done for the semi-targeted analysis, and where the proteins are known, but exact proteoforms are not known. Multimers, the are known, but their like identity of subunits are unknown, so something like that. And so the data acquisition is often done manually because now we are dealing with low throughput and oftentimes using very limited target information, just range of the mass from here to there, something like that. And for the fragmentation, people tried multiple fragmentation at the same time to increase the sequence coverage. So the data analysis often become very challenging because two reasons. So, okay, two reasons. And that I will show later. So the typical input to the data analysis for sure MS2 spectrum, in many cases just a single spectrum or a few spectrum, and also the target protein information. And the output is the proteoforms that yielded the spectrum as a starter, because after that we go to the structure and try to get more information. And so the typical approach is we start with the precursor mass, which can be the summation of different proteins or modified proteoforms, and guess the candidate proteins. And we match the candidate proteins against spectrum, like one by one. So sometimes it can take months to reveal the identity of protein. So conventional database search engines fail because of these two reasons. The first one is the precursor mass is not related to the protein mass, and also we have a bunch of different ion types. It complicates the analysis of MS2 spectrum analysis. So we suggest a solution basically by reviving legacy technique, which is de novo sequencing tags. So tags is really old technique, but it has very good characteristics. The first one is they do not suffer from precursor mass. We can make use of precursor mass, but we can skip to use precursor mass. And also it's quite robust against ion types because only the relative positions among peaks are used, right? And luckily for the top-down high-quality MS2 spectra, in most cases, we have length tags. So we suggest this workflow. We start by deconvoluting the MS2 spectrum in top-down. So now the deconvolution is simply generating the monoatopic masses of the fragment ions. It's quite different from the DIA case. And from the deconvolved MS2 spectrum, we find the tags, and we generate the list of tags here. And we also bring this proteome database, and sometimes we generate target decoy and simply just database search using tags. and we find the reliable list of matched proteins. So quite straightforward. Just one special thing about ion type robustness and precursor mass dependency. This is how we work. So basically, from the peaks, we generate we connect these peaks with amino acid mass difference, and on top of that, we also connect all the peaks from the source. So in this way, basically, we can remove the dependence to the ion type, and we do not have precursor mass ions, so we basically connect all the peaks to the imaginary mass of infinity, and then all vertices finding all paths from the source to sink corresponding to find all the sequence tags. And because we do not want to generate all the tags, because sometimes tags are just too short and they're very, very low score, we can speed this up simply by extending the graph by adding more dimension corresponding to a cumulative score and a cumulative length. And by finding all paths that ends at the sink of specific score and length combination, we can find all the paths that we want quite quickly. And this FLASHTagger is implemented as a web app in FlashViewer web app, and it implements the FlashDecon plus FLASHTagger pipeline for quick deconvolution and protein ID. And the visualization also allows you to look into the raw signal. So we validated our method with sigma antibody standard. Basically, this is a single ECHD MS2 spectrum from precursor mass of 150 kilodalton. And FLASHTagger successfully reported both heavy and light chains. So in the figure in the top left side, we have the reason where tags were found. In the right side, the annotation of the peaks. And interestingly, here we find some tags, even though we do not find any annotation from the intact protein. And here as well, we find a lot of tags, but in the corresponding area, we do not find any annotation. That's simply because there were actually some hidden modifications, and because now we know the location of tags, and by simply compare between the location and the protein mass, we can pinpoint which PTMs that were not specified beforehand. And also we have different ion types. And secondly, we also tested the tool with C-terminal modified E. coli aquaporin Z protein. It was, I think, trimer, yeah. So we targeted trimer of this aquaporin, and we searched it against whole E. coli protein at 1% FDR, and it output 2 hits. The left side is actually the CETA modified aquaporin Z, which is our target, and the right side, this is unmodified aquaporin Z. And because we also make use of the location of tags, in the right side we do not find any CETA tag, and we find a lot of different ion types and also modifications. So to conclude, FLASHTagger successfully identifies target proteins from the NTDMS datasets without using precursor information and without using ion type specification. And this enables the change of paradigm in the top-down MS data analysis, because usually they started with precursor mass, but now we can start from identified proteins to explain the detected precursor mass. So this is very efficient and very fast, and my colleagues were so happy because now they can identify proteins within the seconds, which took like months, or actually it took like 2 years for some cases. So yeah, they're happy. And proteoform characterization is also needed because so far it's just protein identification. It can be done basically just by looking at the position of text, but actually we implemented this proteoform characterization algorithm already, and we found that tags play a very crucial role to speed up this characterization, because somehow tags can anchor the points where you don't want to like explore too much in the space of modification. And also we are trying to optimize FLASHTagger for high throughput proteoform ID in just regular top-down. It's almost done, but I think we found that we need a complementary protein filtration scheme on top of the tagging. So for this work, I would like to thank to my PI, Oliver, and my good colleague, Tom, here, and also my colleagues in Yale University, especially Dr. Won-hyuk Chung. He contributed so much. And also, yeah, Gerard in University of Nebraska, Lincoln. and also our colleagues in university in Australia, and fundings. Thank you so much, and I will have any question.